We often think of Earth's history in terms of explosions, meteor strikes, volcanic firestorms, mass extinctions, dinosaurs thundering across the land, and humans rising just recently to change everything. But between the chaos, hidden in a quiet stretch of geological time, somewhere between 1.8 billion and 800 million years ago, Earth did something strange. It slowed down. No mass extinctions, no snowball Earths, no dinosaurs, bugs, forests, or continents crashing wildly into each other. Just a hush across the planet, a billion-year lull. Scientists call it the boring billion. But there's a problem with that name. Because when you zoom in, you realize this wasn't a pause. This was construction, slow, silent, and deliberate. The Earth wasn't at rest. It was at work. By the time the boring billion began, Earth was already a teenager, about 2.5 billion years old. That's old enough for stability, but young enough to still be finding out what it wanted to be. Let's rewind just a little. Before this calm phase, Earth had been chaotic. There was fire from the skies, constant bombardment by asteroids, boiling oceans, poisoned air, and eventually the rise of tiny organisms, invisible but powerful cyanobacteria, the planet's first oxygen makers, had just pulled off the greatest flip in Earth's history. The Great Oxidation Event. They pumped oxygen into the atmosphere, and in doing so, they killed off most of the life that couldn't handle it. It was a crime scene wrapped in innovation. But after all that turbulence, Earth now entered a peaceful phase. The tectonic plates calmed. Climate was stable. Volcanoes cooled in number and frequency. On the map, long before nations and borders, Earth's first true supercontinent, Columbia, had formed, locking its crust into a sleepy embrace. It was not spectacular, but it was essential. Earth had stopped fighting. It had started building. Now picture this. You look down on Earth from space. There are no blue oceans like today, more greenish, maybe even cloudy. Not because of pollution, but because of life, microbial life. Across the coastlines, stromatolites, layered mounds built by cyanobacteria, carpeted everything in sight like living pom-poms. There are no fish, no trees, no bugs, no animals of any kind. The land is barren. It's rocky, brown, red, and gray. Occasional volcanic ridges mark the horizon. The air is thin in oxygen and rich with nitrogen, carbon dioxide, and the faint smell of sulfur. But everything is calm. Earth is like a massive laboratory, still, stable, and covered in experiments running for millions of years, from one tide to the next. The oceans are alive, but quietly, invisibly. Now, if you could dive beneath the surface, not into the water, but into the DNA of life itself, you'd witness something astonishing, a revolution brewing at the molecular level. Life was not stagnant. Microbes were evolving, just not in ways obvious to the naked eye. The boring billion saw life evolve the most game-changing system in biology, the eukaryotic cell. Unlike the simpler prokaryotes, which are just bare creatures of DNA and membrane, eukaryotes evolved nuclei, organelles like mitochondria, and the ability to function in more complex and specialized ways. This was massive. We're talking about the very foundation of all complex life. Without it, no animals, no plants. Oh, you also, during this time, there was the quiet emergence of, drumroll, sexual reproduction. Yes. This was the billion years where sex began. Before it, life copied itself by cloning. Simple, fast, predictable. But sex added chaos. Shuffle, change, risk, possibilities. It seems ironic. In a time so boring, life threw down the wildest evolutionary card it had. So why didn't all this progress result in strange alien creatures 1.5 billion years ago? One word: oxygen. You see, even though cyanobacteria kept releasing oxygen, it didn't fill the atmosphere. Why? Because Earth was still capturing and trapping it. Rocks absorbed it. Iron stole it. Sulfur cycles neutralized it. The oceans were saturated, what scientists call anoxic waters. Many parts were even euxinic, full of hydrogen sulfide, like a stinky toxic soup. It was only in small oases near the surface, perhaps along photic zones, where oxygen levels reached anything useful. It wasn't until much later that oxygen finally took over fully. But during the boring billion, these slow chemical shifts were quietly redrawing the map of life. Let's talk tectonics. After Columbia came Rodinia, another supercontinent, just as sleepy. It formed through slow-motion collisions of continental cratons, massive ancient chunks of crust, no dramatic mountain chains. No sudden volcanism, just slow, patient assembly. Rodinia wasn't a single giant blob either. It had strange configurations, like blobs of land tied in knots, ringed with ancient seas that acted like Earth's simmering kitchen. These long-lasting landmasses helped recycle elements through erosion, spilling phosphorus and iron into the seas, feeding microscopic life. Plate tectonics during this period operated like a glacier, powerful, but almost imperceptibly slow. Even so, it was these very forces that ultimately led to the shaping of future Earth. For years, scientists dismissed this era as boring. Why? Because fossils from this period are rare, simple, and small. Not the showstoppers of the Cambrian explosion, just microbial mats or hints of early multicellular algae. It wasn't dramatic. It was humble, but slowly, as new techniques evolved, like radiometric dating and isotope tracing, we've uncovered rich stories even in these boring rocks. Tiny shifts in carbon isotopes hint at changing life cycles. Subtle structures show the diversification of eukaryotes. Deep in the Canadian Shield, Australian outbacks, and Russian sedimentary basins lie whispers of forgotten innovation. The past wasn't lost, it was just quiet. The name boring billion was first used as shorthand by frustrated geologists struggling to find big environmental swings or fossil changes, but many now argue it wasn't boring. It was just difficult to detect. After all, what's more dramatic? The meteor that kills or the silent breath of oxygen rising over eons? This billion-year stretch stabilized Earth systems, mild climates controlled atmospheric pressure. Steady carbon cycles, evolutionary experimentation, it was, in many ways, Earth's rehearsal before the grand show. In our fast-paced modern world, it's easy to think value lies in action, speed, and flair. But the boring billion reminds us that slow change is still change, that stable conditions create breakthroughs, and that life's greatest tools were forged in quiet. Patience, that eukaryotes, oxygen, sex, stability, all born, not in chaos, but in the calm between storms. As our chapter closes, Earth stands on the edge of transformation. The oxygen levels are finally climbing. Rodinia will break apart. Climate chaos and snowball Earth lie just ahead. And in just a few 100 million years, life will explode into forms with shells, teeth, eyes, and legs. But remember, none of it could have happened without the billion years of deep breath, deep time, and silent construction. Let's make it clear. For most of Earth's history, microbes weren't just around, they were everything. Think kings, queens, empires, but microscopic. And during the boring billion, from about 1.8 to 0.8 billion years ago, they absolutely owned the biosphere. There are no fish, no insects, no animals, no grass, trees or fungi, just an empire of microbes, living in colonies, cooperating in complex ecosystems, and quietly shaping the planet from the ground up. Voiceover. Tip. If Earth was Netflix, this era ran the longest series ever, and the entire cast fit in a raindrop. Our microbial superstars this chapter. One name you need to know: cyanobacteria, also historically called blue-green algae. even though they aren't algae at all. Cyanobacteria created one of evolution's most powerful hacks: photosynthesis. They took sunlight, water, and carbon dioxide and produced something utterly disruptive: oxygen. And they didn't just produce oxygen by accident, they transformed Earth with it. But during the boring billion, that oxygen didn't yet flood the atmosphere. No, it was absorbed, trapped, bound by iron in the oceans, and stolen by chemical reactions. Still, these quiet green microbes kept going, day after day, tide after tide, century after century. They were builders by nature, patient and persistent, and over time, their communities created structures like none the Earth had ever seen. Now let's talk monuments. Pyramids, castles, skyscrapers? No, long before those existed, microbes built the planet's first cities, called stromatolites. Visual suggestion: time-lapse of ancient microbial mats creating layered domes. Stromatolites form when cyanobacteria grow in layered sheets, sticky with mucus that traps sediment. Over time, layers build on themselves, stacking like pancakes hardened by minerals. Today, we can see fossilized stromatolites in ancient rocks, some over 3.4 billion years old. But during the boring billion, stromatolites were everywhere. They carpeted the shallow oceans, tidal zones, and brackish lagoons, living rocks, slowly rising and falling like microbial breathing. To the casual eye, they were just lumps. But to early life, these domes were cities, teeming with millions of microbes working together. Voiceover suggestion: if we could shrink ourselves down and walk inside, we'd find bustling corridors of light-harvesting workers, anaerobic scavengers, nitrogen fixers, each with a job, each playing a role. Here's the million-dollar question. If all life was microbial, did anything interesting really happen? Or were we just watching pond scum for a billion years? Turns out, mind-blowing things happened, but not in size or forms, in complexity of function. Microbes don't have brains. They don't have legs or eyes, but they communicate. They react. They adapt at molecular speeds. Take quorum sensing, a way for microbes to detect population size and collectively decide to activate behaviors like light avoidance or toxin release. So that's group intelligence, and it's ancient or horizontal gene transfer and a microbial superpower, where they just swap DNA like trading baseball cards. This isn't evolution by reproduction. This is evolution by innovation. Voiceover rule: it's not that Earth stood still. It's that life figured out better ways to move from within. Now, zoom out just a bit. Let's look at how microbial life took over Earth's biosphere. Just like plants today feed insects, which feed birds, which feed wolves, ancient microbial communities had their own ecosystems and food webs. In the ocean, layers formed according to energy and chemistry. Top layer, oxygen producers, cyanobacteria harvesting sunlight. Middle layer, facultative microbes, switching between oxygen and sulfur metabolism depending on conditions. Bottom layer, anaerobes, deeply primitive organisms that hated oxygen but thrived on methane, sulfur, and ancient chemistry. Each layer depended on the waste of the one above, a microbial circle of life. Metaphor for viewer. Picture the ocean like a lasagna of invisible life, each layer stacked with organisms tuned to survive an exact chemical window. Biogeochemical cycles, like carbon and nitrogen, didn't just exist. Microbes invented them. Microbes weren't just living in their environments. They controlled them. One of the greatest mysteries is why Earth stayed stable enough for life to evolve. No runaway greenhouse effects or atmosphere collapse. Answer: microbes. Cyanobacteria regulated carbon dioxide by locking it away in sediments. Sulfur-reducing bacteria helped cleanse oceans of toxins. Methanogens warmed the early Earth. During a dimmer sun, microbial mats acted like planetary Thermostats, we owe our modern climate's beginnings to bacterial feedback loops. So while continents drifted and oxygen trickled, it was cyanobacteria calling the shots from tide pools and lagoons. Then, something big happened. About 1.6 to 1.2 billion years ago, deep inside this microbial world came the game changer, the eukaryotic cell. You wouldn't see it unless you had a microscope. But this cell was packed with features that would eventually shape all animals. Plants, fungi, everything we call complex today. How did it happen? A microbial merger. One cell engulfed another, probably a small energy-producing bacterium. But instead of destroying it, they bonded. That engulfed microbe became the first mitochondrion, an internal power generator. This merger changed everything. Eukaryotic cells could get bigger, more flexible, specialized, and more durable. It was like upgrading from a bicycle to a spaceship. Voiceover cinematic comparison. If microbes were peasants, the eukaryotes were knights, heavily armored and capable of exploration on a different scale. It didn't stop with eukaryotes. Soon, perhaps around 1.2 billion years ago, life began experimenting with multicellularity. That's right, not by accident, but on purpose. Colonies of related cells began working together permanently. Early multicellular algae appeared, like Bangiomorpha, possibly the first sexually reproducing multicellular eukaryote. This was teamwork at the cellular level. It may not have looked like much, just filaments, slime chains, floating mats. But the leap was historic. Earth's biosphere was no longer just single cells or clusters. It was slowly assembling the ingredients for organs, tissues, and species you'd recognize today. If you want to see proof of this microbial empire, you won't find dinosaur bones, you'll find chemical fingerprints, carbon isotopes showing microbial respiration, lipid biomarkers, fossilized fat molecules, tied to eukaryotes, molecular clocks embedded in DNA pointing to ancient diversification. In places like the Gunflint Chert, Australia's Pilbara, and ancient Siberian rock formations, we find fossils of microbial filaments, mats, and even rare signs of cell division frozen in time. These rocks are like diaries, updated silently for billions of years, and every page says the same thing. The microbes never stopped ruling. They just gave us life's blueprint. We often romanticize the big beasts of evolution, dinosaurs, mammoths, whales. But without the almost 1 billion year reign of microbes, none of that would have been possible. Let's rewind to just before the boring billion began. About 2.4 to 2.0 billion years ago, Earth's surface was nearly alien. No breathable air, oceans choked with iron, atmosphere full of methane, CO2 and sulfur gases, but then out of nowhere, everything changed. Cyanobacteria, already practicing photosynthesis, began releasing oxygen into the atmosphere. This moment is known as the Great Oxidation Event, or GOE for short. Voiceover idea. Suddenly, Earth had a new player on the stage. A molecule as reactive as it was revolutionary. Oxygen may seem small, but it's chemically dangerous. It corrodes, burns, and breaks molecules apart. So when it showed up, early anaerobic microbes started dying. Earth underwent a mass extinction, but only for its invisible rulers. Oxygen was now in charge, or so we think. Here's the strange twist. After the GOE, we don't see continued oxygen buildup. In fact, geological records plateau. For over 1 billion years, the oxygen level stayed strangely low. Just fractions of today's atmosphere. Not enough to support animals, not enough to form an ozone layer, not enough to dominate the oceans. Voiceover buildup. The planet's breath had started, then paused, as though Earth was suffocating itself on purpose. Scientists wondered, where did all the oxygen go? Turns out Earth wasn't ignoring oxygen. It was absorbing it, everywhere. During the boring billion, oxygen didn't vanish. It was trapped, buried, or neutralized by A-banded iron formations. BF's oceans were rich in dissolved iron, Fe2+. When oxygen met iron, it oxidized instantly, forming rust. This rust dropped to the seafloor and built up in layers. That's how you get banded iron formations. Layered red and black stone deposits still mined today. Visual idea. Cross-section animation of ocean rusting over time. Building deep iron layers. B. Volcano gases. Volcanoes pumped out reducing gases like hydrogen and methane. These reacted with O2, removing it from the air. Every volcanic eruption undid some of life's progress. C. Ocean chemistry. Oxygen can't just float freely in water. It reacts immediately with sulfides, methane, and early sediments. This prevented oxygen from rising atmospheric levels. Takeaway metaphor. It's like trying to fill a leaking bucket. Oxygen was being poured out, but Earth kept poking new holes. But there were rare exceptions. Local environments where oxygen levels did spike. These were called oxygen oases. Small pockets, likely in shallow coastal waters. Where sunlight was strong, microbial activity was high, and oxygen stayed long enough to make a difference. For primitive eukaryotes, early complex cells, these were hotspots of evolution. But globally? Not enough. These were candles in a dark cave and not a sunrise. Voiceover suggestion. Evolution lit the match. But the winds of geology snuffed it every time. With atmospheric oxygen stuck at low levels, maybe just 1 to 2% of today's amount, life stayed small. Why? Because oxygen is energy. More O2 means more efficient respiration. Organisms can build muscles, nerves, movement, complexity. With less oxygen, cells stay small, metabolism stays slow, no large animals, no predators, no fast swimmers or flyers, just microbial mats and floating algae. Voiceover line. Imagine building a skyscraper with only enough power to run a flashlight. So how do we go from tiny oases to a world bursting with life? Scientists now believe there were trigger mechanisms that broke the cycle. Other supercontinent shifts. When Rodinia, the silent supercontinent of the boring billion, began to rift and break apart, around 800 million years ago, it caused new shorelines, more erosion, more nutrient flow, more phosphorus in oceans, key for oxygen-producing microbes. B. Biological feedback loops, more nutrients, more photosynthesis, more oxygen, more diversity. This ultimately shifted the chemical balance where oxygen production finally outweighed oxygen loss. Earth had tipped. The long pause was over. One of the weirdest and most revealing clues comes from a period called the Lomagundi excursion, 2.2 billion years ago, slightly predating the boring billion. It showed a brief oxygen spike in carbon isotopes, suggesting Earth tried to go fully aerobic, but failed. After Lomagundi, oxygen levels crashed, metabolisms cooled. The planet slid back into near anoxia for centuries. Voiceover line. Earth wasn't fighting life. It just wasn't ready. Another chemical detective in our story is sulfur. By studying sulfur isotopes, scientists can determine redox reactions in ancient oceans. When oxygen is low, sulfate-reducing bacteria dominate. They leave behind unique sulfur signatures. Data shows these bacteria ruled most of the ocean during the boring billion. This means vast stretches of Earth remained euxinic, rich in hydrogen sulfide, toxic to most eukaryotes. Translation for viewers. The ocean was more like a hot tub of rotten eggs, not a garden of evolution. Finally, near the end of our billion-year saga, small, steady steps began to add up. Despite all the reactions working against it, oxygen levels rose to about 10–15% of modern values by 800 million years ago. Still low, but enough. Enough for ozone formation, filters UV radiation, enough to allow larger cells, enough to open the door to multicellular life, and What a door that would be. Shortly after comes Snowball Earth, Neo-Proterozoic Revolution, Cambrian explosion, but none of it, none, could have happened without waiting. And waiting, and waiting, narrators close. The great oxygen wait reminds us that evolution doesn't race toward complexity. It pushes, rests, adapts, and sometimes stalls for 1 billion years. In this long lull, microbes didn't just survive. They filled every gap, tested every limit, and laid the foundation of breathable life. And when oxygen finally passed the tipping point, Earth took a deep breath, and life changed forever. Closing visual idea, animatic of oxygen levels, slowly ticking up over billions of years, with microbial life in the background, growing more diverse. A timer counts slowly, then, boom, a flash of light as Earth's oxygen rises, and multicellular life begins, travel back in time, around 1.8 billion years ago, give or take a few million. The Earth looked nothing like what we see on globe maps today. In fact, if we had a time-lapse, continents would shift and reshape like clouds. But during the heart of the boring billion, a special kind of landmass formed. A supercontinent, Columbia, also called Nuna. Not just a continent, but a gathering of all the world's major crustal plates. Narration tip. Think of Earth like a cracked eggshell. Over time, the pieces move, shifting restlessly, combining and breaking over eons. Most scientists agree that Columbia, or Nuna, came together around 1.8 billion years ago. From North America and Greenland to parts of Siberia, India, and Africa, Columbia unified the planet's fragmented lands into one vast, dry, barren mass. But don't picture lush forests or birds and trees. Columbia's surface was wearied by billions of years of erosion. The skies above, mostly empty. The weather, probably hot and arid in the interiors, wetter at coastal edges. No flowering plants, wind, rock, and microbial crusts. Still, this supercontinent was more than a chunk of rock. It was an architect of the entire biosphere. It might not be obvious, but supercontinents control the climate in ways few other geological phenomena can. How? Position affects solar radiation. If continents cluster at the equator, they reflect less sunlight and stay warmer. At poles, more ice, more reflectivity, colder climate. Mountains weather into rivers that deliver nutrients, like iron and phosphorus into oceans, energizing microbial life. Tectonic calmness during supercontinent stability means fewer catastrophic volcanoes, but also less geological stimulation. Voiceover comparison. Continents are like thermostats. Shift them 1 degree, and the world freezes or burns. During the boring billion, Columbia was geologically quiet. Volcanoes were limited. Erosion was slow. Nutrient supply to oceans was low. This starved the seas, limiting oxygen production and biological innovation. It's not that Earth couldn't evolve faster, it was missing the fuel. When inland areas erode, they feed dust, minerals, and sediments into the sea. This gives life essential nutrients. Phosphorus, crucial for DNA, RNA, metabolic reactions, iron, vital for photosynthetic processes, calcium and magnesium, needed for early cellular structures. But during much of the boring billion, with Columbia intact and relatively flat, erosion slowed dramatically. Less sediment in rivers meant fewer nutrients. Fewer nutrients meant fewer microbes. Fewer microbes meant slower oxygen buildup. This is among the top theories for why the boring billion was so biologically quiet. It wasn't boring, just underfed. Alternate metaphor. Imagine a world-sized aquarium with amazing fish and coral, except you barely feed them. They don't die, they just stop growing. To understand how different Earth was back then, we need to talk plate tectonics. Earth's interior is molten. The crust rides on this flowing mantle like cracked puzzle pieces sliding across lava. During the boring billion, tectonic movement slowed. Why? Several reasons. Mature crust. Much of the crust had cooled and stabilized. Lack of major collisions. With Columbia formed, continents weren't smashing together. Stagnant lid hypothesis suggests Earth may have gone into a low-energy tectonic mode. This lack of internal planetary drama left surface life with few new challenges or novel ecological niches to evolve into. Voiceover comparison. Without tectonic drama, Earth gave evolution a blank notebook, but no pen. But just because things slowed down doesn't mean they stopped. In coastal inlets, shallow seas and rift basins at the edges of Columbia, new forms of microbial life may have proliferated quietly. Places like the Belt Supergroup, North America, the MacArthur Basin, Australia. Russia's East European platform, these were warm, shallow marine environments, calm, chemistry-rich, and perfect for the evolution of early eukaryotes. Again, Earth's silence wasn't a failure. It was a retreat, a pause, a deep breath before charging evolution forward. As we progress toward 1.1 billion years ago, Columbia begins breaking apart, and a new supercontinent forms, Rodinia. Rodinia is different from Columbia. It's larger, formed slowly from fragments of previous continents, more complex, with internal rifts and varied strategies for evolution. Rodinia existed through the late Mesoproterozoic into the Neoproterozoic era, and its formation likely changed everything for life. Here's why. Mountain building began again. More erosion. Tectonic rifts allowed mineral-rich basins to form. More rivers fed phosphorus into the ocean's oxygenation. Events followed. Rodinia created the geological unrest that had been missing for 700+ million years. Eventually, 750 to 650 million years ago, Rodinia began to split apart. And when that happened, climate chaos, ocean current disruption, nutrient slurry floods the seas. Oxygen finally surges toward modern levels. This stability breakdown cycle explains much of early life's rhythm. A poetic way to say it. First Earth settles, then oceans stir, then lightning strikes in DNA. Within a few million years after Rodinia's breakup, Earth would face snowball, Earth episodes, massive oxygen spikes, the Ediacaran fauna, and finally, the Cambrian explosion, where evolution would go wild. None of these were possible without the supercontinent, cycles quietly driving the gears. Scientists have identified at least 3 to 5 full supercontinent cycles over Earth's time. Canorland, Toitu Setegay, Columbia, Nuna, 1 Gay, Rodinia, 1 Gay, Panotia, 600 Me, Pangaea, 300 Me. The cycle is roughly an 800 million year beat, like Earth itself has a geological heartbeat. Assemble, drift, break apart, reassemble. Each cycle resets climate, oxygen levels, biodiversity, ocean chemistry, and weather systems. Voiceover line. Evolution didn't sprint. It marched to the beat of drifting continents, hidden in footprints we only now begin to see. So what's the takeaway for your audience? During the boring billion, the land masses weren't fighting each other. They were resting. Oceans were shallow, stratified, and full of chemical stories. Erosion was lazy. Oxygen trickled. Life was patient. But without Columbia's quiet or Rodinia's revival, the Earth we know, full of trees, bees, birds, and brains, couldn't exist, because sometimes staying still is part of the plan. Every time the continents moved, they sculpted DNA. Voiceover line. Evolution didn't sprint. It marched to the beat of drifting continents, hidden in footprints we only now begin to see. Before anything with a spine or a shell, before insects spun silk or T-Rex roared, there was this. The Eden of the single-celled Earth's surface was dotted with small landmasses, watched over by calm skies. shallow seas, and no forests. On land, barren rock; in the water, green film, microbial mats, floating algae. No predators; there were no food chains, no jaws, no eyes, legs, or war. Instead, life existed in a long, chemical conversation with its environment. Everything revolved around sunlight, mineral availability, energy efficiency. Voiceover: in this perfectly balanced, low-energy ecosystem, survival wasn't about strength. It was about harmony. The flat coastal regions of Earth became colonized by one of life's greatest engineers: microbial mats. No, not plants. Not animals. Layers of microbes, mostly cyanobacteria, forming slimy blankets that coated wet rock surfaces and sea floors. These mats were self-sufficient, anchored by sunlight layers thick, creating internal ecosystems stable. For millions of years in a single spot from orbit, the shorelines would seem green. But not from vegetation, from sheets of living film. Visual animation idea, zooming into a mat layer to reveal various microbes interacting. Photosynthesizers on top, anaerobes below. These mats ruled the world. The coral reefs, forests, and fields of the boring billion. Non-competitive, non-violent, a living blanket of peace. Here's the key question. Why wasn't there conflict? A. No predation had evolved. At this point, no life form had evolved the tools to hunt, chase, paralyze, digest. Other complex living cells' single-celled energy systems were limited. No mitochondria yet, no nervous systems. No movement tools like what we'd associate with predators. B. Low oxygen. Low metabolism. Everything had to work slowly. Without adequate oxygen, energy was precious and rare. Quick movement or energy-intensive hunting. Not possible. Life didn't fight because it literally couldn't yet. Voiceover: with just enough fuel to survive. Cells learned patience, not power. Another surprising reality? The boring billion may have favored cooperation over selfish competition. Many early microbial communities worked symbiotically. One microbe's waste became another's food. Layered oxygen gradients allowed various metabolic zones. No need to compete. Niches were chemically defined. Even the eukaryotic cell itself, Earth's miracle of biology, began with merger, not murder. Quick explainer. A larger cell engulfed a smaller energy-producing bacterium, mitochondrion, in a mutual agreement, sparking the creation of all complex life. Voiceover idea. The most important invention in history wasn't built with fire, but friendship. This was Earth's first golden age of symbiosis. Try to imagine it. No fight or flight response, no hiding, no enemies, no hunger for flesh. Every cell drifted, sat, or slowly attached to biofilms. Chemistry was the battlefield, not teeth. If you visited a shallow sea, you'd hear no sound, see no motion, just carpets of green slime and softly glowing plankton in the tide. Narration tip: cinematic pull. It was Earth's quiet garden, untouched by predators, wild with potential, yet controlled by the rules of sunlight. So how did evolution happen at all? Life didn't evolve outward. Limbs, senses, scales. It evolved inward. Stronger DNA, repair mechanisms, organelles to manage cell activity, expansion of mitochondrial features, development of the nucleus, genetic HQ, more sophisticated membranes and regulation techniques, and, perhaps most important of all, sexual reproduction. Instead of cloning, some early eukaryotes evolved meiosis, allowing them to mix genes, shuffle mutations, create offspring better suited for environmental shifts. Voiceover line. Instead of fighting competitors, early life learned to multiply its options. This peaceful era gave life the time and stability to build genomic libraries, collections of genes that could be activated later when oxygen and food chains changed the game. Today, many of the genes we use for functions like development, communication, cellular differentiation, all seem to trace roots back to this peaceful time. Narration comparison. Like monks transcribing knowledge through long winters, microorganisms wrote the blueprints of biology long before the age of monsters. Because they didn't need to survive war, they built for the future. 8. What would Earth have looked like? Here's a narrative segment to visualize this chapter. Scene scroll, suggestion, 3D journey. A camera floats over the coastline of a supercontinent. The land is bare. Orange-red cliffs, basalt flows, empty beaches. We dip below the waterline. The view becomes greenish. Temperature warm. Visibility low. The seafloor is not crowded by coral or fish, but instead coated in vast soft fields of microbial mats. No movement, no sound. Zoom in. Millions of microbes pulse slowly, cycling sunlight and nutrients. Very few bubbles rise nightfalls. Bioluminescence flickers across the tide, not from jellyfish but from colonies of glowing plankton. Voiceover, soft. 1 billion years of magic. Visible only to a microscope. At the end of the boring billion, as oxygen began to rise and new niches emerged, predation, for the first time in Earth's history, evolved. Amoeboid grazers began nibbling on bacteria. Larger cells engulfed smaller ones. Defensive strategies appeared. Harder membranes, toxins hiding behavior, and once predator versus prey erupted. Evolution went into overdrive. But contrast that predator-rich world with what came before. 1 billion years of equilibrium-shaped cells with cooperation, resilience, and complexity, not teeth. Voiceover line, violence created diversity, but peace created the tools to survive it. Here's how we tie this all together for your audience. Despite its name and stillness, the boring billion wasn't a dead end. It was a laboratory, a workshop, a monastery. Without chaos, conflict, or extinction events, cells perfected internal chemistry, built genomes slowly and richly, tested cooperation instead of combat, prepared for the oxygen-rich revolution that was coming. Closing words. In the age before fear, life was free to dream, Earth was quiet. And in that silence, evolution found patience, balance, and the seeds of everything that would roar to life. For over 2 billion years, life on Earth had been simple. Cell walls, basic DNA, chemical reactions. Repeat. The majority of organisms were prokaryotes, tiny, single-celled microbes without nuclei or organelles. They dominated Earth by the trillions, but next came something radically different. Something bold, complex, ambitious, the eukaryotic cell. Voiceover comparison. If prokaryotes were motorcycles, eukaryotes were starships. Let's break this down simply for your audience. A eukaryotic cell has a nucleus, where DNA is protected and managed. Mitochondria, inner powerhouses that generate efficient energy. Internal membranes and compartments, specialized for tasks. The ability to get much larger and more versatile, and this was revolutionary. It allowed cells to store more DNA, do more things at once, specialize, communicate, and even prepare for multicellularity. Voiceover line. The eukaryotic cell was biology's first skyscraper, stacked, complex, and ready for expansion. How did eukaryotes evolve from simpler life? The leading theory is quite legendary in microbiology, endosymbiosis. Here's what likely happened. A large prokaryotic host cell engulfed a smaller bacterium. Instead of digesting it, the two began working together. The engulfed bacterium became a mitochondrion. Over millions of years, they became inseparable. The smaller partner evolved to power the host. The host gave it shelter. Great animation idea. Inside a cell, 2 organisms face off. Dialogue like, "Join me, and I will make you more powerful than you can imagine." This unlikely partnership, not warfare, created the powerhouse that enables all multicellular life to breathe energy into motion. Voiceover gem. Not an invasion, not a conquest, a cosmic collaboration. Why was this such a big deal? Mitochondria gave cells access to 18 times more energy than traditional metabolism. That led to larger cells, longer lifespans, more DNA room, more genetic creativity, cellular compartmentalization. Suddenly, a single-celled organism could afford to have complex gene regulation, develop new internal structures, outsource different jobs to different organelles. Voiceover note: mitochondria were the jet engines that finally let life lift off from the tide pool. Apart from mitochondria, eukaryotic cells developed A. The nucleus, DNA housed inside its own membrane, protected, organized and regulated. B. Endoplasmic reticulum and Golgi bodies managed proteins, folded them like origami and packaged them like a factory. C. Cytoskeleton gave structure and helped with movement, tremors of the first arms and legs. Visual idea. Beautiful animation of a cell interior building itself like a futuristic city, pipes, tunnels, energy generators, communication towers. Where did these first eukaryotic pioneers emerge? Most likely in warm, shallow marine basins rich in nutrients and low in oxygen, a Goldilocks zone. Possible locations in modern geography: the Belt Supergroup, Montana, Z, the MacArthur Basin, Northern Australia, India's Vindhyan Basin here. Microorganisms experimented with forms unseen before. And over time, 2 billion years into Earth's history, eukaryotic life began to spread. Voiceover. The silent revolution wasn't televised. It was fossilized. Let's introduce your audience to some actual known players. A. Gripania spiralis, possibly 2.1 billion years old spiral-shaped fossil. A. Probable eukaryotic alga. B. Angiomorpha pubescens, angiophyte. Billion years ago, first evidence of sexual reproduction, clear signs of multicellularity. Resembles red algae like modern-day seaweed. This may have been the first organism to split roles among cells, such as parent and offspring. C. Acritarchs tough-walled. Microfossils widespread in the Proterozoic, diverse shapes hint at biological experimentation. Voiceover. These were the blueprint drafters, the engineers of multicellular life, still invisible but playing with possibilities. One of the biggest byproducts of the eukaryotic revolution? Sexual reproduction. Instead of simple binary fission, cell splits in two, organisms could now shuffle DNA, combine favorable traits, create offspring with genetic variation. This massively accelerated evolution. Suddenly, life wasn't just repeating what worked. It was constantly remixing genes, anticipating change, faster than natural selection alone. Life began self-engineering. Voiceover line. Complexity thrives when you exchange ideas. Even in biology. At some point, cells didn't just cooperate within, they began sticking together. Multicellularity likely evolved multiple times, independently, in red algae, green algae, fungi-like protists, potentially early animal ancestors, to not every cell in these early multicellular organisms was the same. For the first time, cell specialization appeared. Some cells for movement, others for defense or reproduction, a body with defined roles, and like an orchestra, playing in tune. Visual suggestion, microscope style. Time-lapse of single-celled organisms, fusing and staying joined after dividing. Narrator. Life didn't grow bigger just to get noticed. It grew bigger to organize, to harmonize, to survive together. So what did the rise of eukaryotes actually accomplish? Let's recap for your audience. Opened the door to internal cell complexity, led to multicellular life, enabled genetic diversity beyond cloning, created true biological innovation systems, forever altered Earth's ecosystems, even under low oxygen, and incredibly, all of this happened during the so-called boring billion. Voiceover close. While Earth slept, cells built futures. No predators, no pressure, no rush. Just chemistry, cooperation, and the birth of complexity. Without a roar, life unlocked its greatest engine, and the age of visible evolution had begun. Let's start with why scientists originally called it the boring billion. Few fossils flatlined atmospheric oxygen levels. No mass extinctions. No big climate shifts, minimal tectonic action. To the mid-20th century geologists, it looked like no biological bursts, no evolutionary progress, no plate movement, no excitement. Voiceover clue. In science, boring doesn't mean nothing happened. It means we didn't yet understand what to look for. And that's exactly what changed in the 21st century. One of the biggest reasons why the boring billion is no longer considered boring: genomics. In the last 20 years, scientists began comparing the DNA of living microorganisms, some still identical to their ancient ancestors. Through molecular clocks, we can now rewind genetic mutations to estimate when important traits evolved. The results? Eukaryotic genes emerged as early as 1.6 billion years ago. Sexual reproduction possibly began over 1 billion years ago. Genes responsible for multicellularity and even nervous systems have deep roots in this quiet age voiceover idea. Even without bones or bodies, evolution wrote blueprints in the dark, and those blueprints survived. This means the boring billion wasn't a pause. It was a prototyping phase hidden in code. Fossils from this era are small, but scientists are now uncovering unbelievable diversity in places once ignored. Where they're found: shales from India's Vindhyan Basin, the Spitsbergen Group in Arctic Norway, Canada's Gunflint Formation, Australia's MacArthur Basin. What's being found: Grypania, possible spiral-forming algae, 2+ billion years ago. Bangiomorpha, red algae, clear signs of sex and multicellularity. E1005 gay acritarchs, bizarre, tough-shelled microorganisms of enormous diversity. Many display elaborate coverings, spines, and warlike biological armor. Voiceover. Why would an organism evolve armor? In a world with no predators? This suggests competition, adaptation, and specialization, even in a predator-free Eden. Maybe they weren't being eaten. Maybe they were fighting each other chemically, for light. Or for territory. Forget bones. The boring billion talks through chemistry. By scanning ancient rocks using cutting-edge equipment like synchrotrons, X-ray diffraction, and isotope mass spectrometers, researchers have found sulfur cycles more complex than previously thought, mid-Proterozoic oceans, with transition zones of rising oxygen-iron formations showing cycles of oxygenation, anoxia, euxinia, and back again. Narrator pull. Like slow tides of chemistry, Earth kept changing under our feet, and every atom was evidence. Even trace metals like molybdenum and nickel, essential for microbial metabolism, show pulses of scarcity and abundance. Meaning, life had to adapt constantly. Just because we don't see teeth or claws doesn't mean there was no conflict. Today, many microorganisms still wage war with each other using toxins, antibiotics, light blocking, films, nutrient-stealing mechanisms, and recent models suggest these invisible biowars were being waged even 1.5 billion years ago in microbial mats. Some even formed protostocks, or armor plates looking suspiciously like primitive structural defense. Voiceover. Predators didn't invent struggle, microbes did. In some formations, like the Gaoyuzhuang Formation in China, fossilized evidence shows clustered repeating patterns, suggesting cell coordination. Combine that with possible directional motion in fossil traces, signs of cell differentiation, clumps of organized cells that resemble tissues, and scientists now believe the behavior of early eukaryotes was far more sophisticated than once thought. Some may have even flirted with proto-neural communication. It wasn't just life existing, and it was life trying new things constantly. Another long-understood concept in evolution is life gets creative under stress. Turns out, the boring billion wasn't purely peaceful. There were plenty of gentle but real shifts in sea level, atmospheric pressure, volcanic, degassing, nutrient flux, massive supercontinent, assembly, breakup events. Each shift acted like a pressure cooker, testing life's ability to store energy, reproduce more efficiently, defend against chemical sabotage, exchange genes faster. Voiceover line. Even with no predators, life stopped coasting and started coding its next escape plan. Recently, evolutionary biologists have discovered genes used in nervous systems, long considered a complex animal trait, actually existed in simple protists. Let that sink in. Your brain doesn't run on brand new code. It runs on recycled molecular software from single-celled ancestors, possibly as far back as 1.5 billion years ago. These genes, called snare proteins and others, allow cells to send signals, wrap chemicals in vesicles, and process stimuli, the primitive building blocks of synaptic activity. Voiceover. Neurons didn't invent messages. Cells had been whispering to each other for 1 billion years. What if we stop calling it the boring billion and instead rename it? Some scientists suggest terms like the era of innovation, the deep evolutionary stage, the prototyping billion, or simply the long genesis, because in this billion-year span, life discovered how to breathe oxygen, perfected cellular cooperation, invented sexual recombination, evolved key proteins used in immune systems, nervous systems, and development. It wasn't a flat line. It was R&D, slow, patient world-building innovation. So what does this all mean? It means that underestimating quiet phases is a mistake, in both biology and history. Even during stillness, life may be writing its greatest algorithms. Innovation may look slow, but it runs deep. Voiceover. Close out, like an artist sketching for decades before picking up the brush. Evolution during the boring billion was preparing the lineages, the tools, the engines, the languages, the ideas, and one day it would unleash them in a spectacle the world had never seen. By 850 million years ago, Earth had spent over 1 billion years in climatic, tectonic, and evolutionary stability. Life was microbial, but quietly innovating eukaryotic cells were spreading, oxygen was finally trending upward, supercontinents had formed, Rodinia, and were beginning to rift. But what happens after such a long period of quiet? Pressure builds. That's exactly what was happening, and geologically, biologically, atmospherically. And that pressure was about to be released in one of the most violent ways possible. Voiceover, foreshadowing, balance, breeds transformation. Just ask a volcano, or in this case, an entire planet. Rodinia, Earth's massive supercontinent during the late Proterozoic, was never built to last forever. Around 800 million years ago, it began to fracture. Large rifts opened between continental plates. What followed? New shorelines formed, tectonic activity increased, volcanoes returned in force, nutrients flooded into oceans, erosion rates skyrocketed. This tectonic breakup played a crucial role in altering climate, ocean chemistry, and ultimately life's trajectory. Here's what this new, fractured Earth did to its oceans. The continental breakup led to increased phosphorus and iron runoff into the seas, more nutrients, more bigger algal blooms, more photosynthesis, more oxygen, increase in organic carbon. Burial. It sounds like things were getting better, right? But here's the twist. This also pulled CO2 from the atmosphere, and less CO2, less greenhouse warming. Voiceover insight. The stage was being set not just for life to evolve, but for the Earth to freeze. Earth in earlier epochs had been hot, humid, and greenhouse-heavy, but with oxygen rising, carbon dioxide dropping, increased cloud formation. More sunlight reflected from volcanic ash and ice. The planet's thermostat began to shift drastically. Enter a climate tipping point. Small glaciers at high altitudes began to spread. Ice sheets formed, stretched poleward. Oceans cooled. Winds changed. Weather systems broke down. Visual idea. Slowly invading ice across a supercontinent. Zoomed out planet turning pale blue. Narration. Earth wasn't panicking. She was recalibrating. This is where we leave the boring billion behind and enter the cryogenian period. And it was anything but boring. Between 635 million years ago, Earth may have experienced multiple full or near global glaciations. Picture this white ice from pole to pole, glaciers stretching into tropical zones, global ocean surfaces freezing sunlight. Bounced back into space, a snowball Earth or slush ball Earth depending on the model. Some estimates suggest ice was up to 1 kilometer thick in equatorial regions. Of voiceover. Earth became an ice-covered pearl gliding silently through the blackness of space. And life, well, it didn't go extinct, but it got creative. Even in this frozen world, early life adapted. Where? Hydrothermal vents, oases of warmth and nutrients in deep oceans. Thin meltwater layers beneath sea ice cracks and glaciers where sunlight could filter. Life went microbial. Small, flexible, versatile. Survival techniques, switching from photosynthesis to chemosynthesis, entering metabolic hibernation, forming symbiotic collectives. These harsh conditions pressured life to evolve, specialize, prepare for multicellularity. On a whole new level. Voiceover. Inspirational. In Nyok, the darkness of Earth's coldest hour, life found the fire within. So, how did Earth recover? It wasn't easy. The freeze lasted millions of years. But beneath the glacial silence, volcanoes still erupted. Volcanic activity continued building up one critical greenhouse gas, carbon dioxide, CO2. Since ice prevented absorption by oceans or rock, the CO2 built up for millennia. Earth's blanket of heat slowly restored. Warming began slowly, ice melted, oceans rose, storms resumed, Earth roared back to life. This post-Ice Age period is often referred to as the greenhouse aftershock, and it came packed with change. As Earth warmed and glaciers retreated, rivers carried new torrents of nutrients into oceans, oxygen levels surged, new coastal shallow water ecosystems flourished, multicellular life accelerated. Notable firsts and consequences. First, animal-like multicellular fossils. Possible emergence of early sponges. Investigations showing signs of early nervous system pathways. The Ediacaran period, right after the Cryogenian, would soon introduce large, soft, multicellular organisms you could finally see without a microscope. The quiet was over. Voiceover. The billion-year breath became the Cambrian shout. Most people point to the Cambrian explosion, p. 540 May, to mark the rise of complex life. But any evolutionary biologist will tell you, it began earlier. The boring billion and cryogenian were the crucible. Lessons learned in those harsh times form the toolkits for all future animals. You can't have complexity without endurance, adaptability, and innovation, all traits life had to develop during Earth's coldest trial. Closing narration, inspiring. The calm before a storm is not truly calm. It's coiled potential, hidden intensity, waiting. The breakup of rodinia, the quiet rise of oxygen, the silent cooperation of microbial life, all came together not for an ending, but a beginning. And when Earth finally cracked its icy shell, the whispers became a roar, and evolution exploded forward. Screen fades to black. One word appears. Bold, rebirth scene. Your ship descends slowly through the atmosphere. You pass alien cloud patterns, strange tinges of green and blue, and a pale sun overhead. There's no human trace. The world is awakening from prehistory. Narration, calm and wonderstruck. You land somewhere near the equator. Not that it looks familiar. You're standing on the shores of an infant continent. Maybe it's part of Rodinia or Columbia before it. The year is 1.3 billion BC. Everything is different. And yet, Earth has never looked so alive. So patient. Scene. Rocky outcrops the color of rust and silver stretch all the way to the horizon. There is no grass. No trees, no birds. The wind howls, uninterrupted. There are only jagged, eroded cliffs, scattered quartz and granite-red dirt. Strange films of life clinging to stones, narration. This world doesn't bloom. It bakes. The land is silent save for the call of wind and the crash of ancient waves. Scene. As you wade into a warm, shallow sea, it's not empty, just subtle. The water is tinted green and gold. Floating particles shimmer. Cyanobacteria form a thin surface scum. Beneath that, life is dense, microscopic, unrelenting. Narration, excited. You're diving into the true empire of the boring billion. The oceans. Because here life owns everything. Not flashy life, but humble rulers. Microbes in mats, colonies, clusters, or creating chemistry that'll change the world. As you swim along the shallow seafloor, you pass over stromatolites, stone-like, domed ecosystems made by cyanobacteria microbial carpets. Layers of oxygen-producing and sulfur-metabolizing life patches glowing faint green. Brown, black, and depending on depth and chemistry narration. These are no ordinary mats. They're cities, tens of thousands of years old, built one cell layer at a time. Oxygen flows upward, sulfur down. A sandwich of evolution. Some of these mats have stood longer than any civilization you can name in the modern world. Take your viewer deep into the unseen. Shrink the camera down until you're looking at single cells battling, dancing, and partnering. You see a drifting eukaryotic cell and larger, complex, glowing softly packs of smaller bacteria swarming nearby, one large cell engulfing another one, but not killing it. The birth of a mitochondrion narration, awestruck. You just watched the invention of energy on a whole new level. This is the silent revolution, no sound, just destiny. Scene, you drift along the current into deeper waters. The ocean goop becomes thicker with life. Floating algal bladders, strands of early multicellular chains swaying in rhythm. You spot simple organisms combining into primitive colonies, one, reproducing sexually, mixing genes in euphoria you can't hear. Another forming a spore to survive upcoming cold narration. There are no eyes here. No claws, but don't be fooled. These organisms are rewriting the biology of the future. They've invented sex, cells within cells, and soon they'll build bodies. Scene. From an elevated point of view, you see the ancient supercontinent stretching across the horizon. Rodinia, half-formed and tectonically tense. Volcanoes bubble at the edges. Rivers bleed red with iron-rich water, feeding seas with tomorrow's nutrients. Narration reflective. These continents moved slowly, but their influence was colossal. Each shift changed the currents, the atmosphere, the chemicals in the sea, and just like that, all of life turned its head to follow. Scene. You look up. The sky is bluish-purple, thanks to different atmospheric gases. No ozone yet. No stars visible during daytime. Clouds drift like sluggish dancers. You inhale, using a filter because you wouldn't survive. Oxygen is rising, but it's still not breathable for a modern human. You'd be gasping within seconds. Narration. You're not supposed to be here, but it's okay when you're just visiting. You're watching oxygen build the invisible staircase to animals, lungs, and language. Scene transitions, fast-paced montage. Drift over the icy poles, quiet and void of life-scanned coastlines filled with strange stromatolites. Hover above equatorial zones glowing with algae. Watch continents crack as Rodinia slowly begins its breakup. You witness time shift. The world quivers with coming change. Narration. Life is learning. The land is splitting. The planet is preparing for a moment of transformation unlike any it has seen. As you tilt Earth forward on its timeline, things begin to shift. Glaciers build in the distance, winds grow colder, clouds disappear, the warmth begins to fade. Narration. The boring billion is ending. But history doesn't end with a scream. It ends with a shiver. You float upward past clouds, past the green-toned skies, into orbit. You look down and see the first arches of ice creeping toward the equator. Voiceover. The calm is over. The world is about to freeze, and underneath that ice, life will prepare to finally bloom. Closing thoughts. Final narration. Full circle. What would it feel like to stand in the silence of the world's deepest past? To watch the ticking of evolution, without a heartbeat or a sound? If you visited the boring billion, you wouldn't hear roars or screams. You'd hear the sound of life. Breathing in. Screen fades to black. Text fades in slowly. Next time, life exhales. Scientists once dismissed this era with a shrug. A placeholder. A billion-year flatline on the evolutionary graph. But as we've just seen throughout this series, that was a misunderstanding, because hidden underneath the monotone, life cracked the code for complexity. Cells invented cooperation, not conflict. Oxygen fought quietly to rise. The land, the ocean, and the atmosphere rehearsed for everything that came next. Voiceover line. The boring billion didn't fail biology. It taught it how to wait. From the boring billion, we learn one of the hardest truths in evolution and in life. Real genius takes time. Here, life wasn't rushing. It was testing the rules of oxygen metabolism, inventing internal DNA management, trying partnership over predation, stockpiling genes for future innovation. Every breath you take today, every neuron in your brain, every cell defending you right now, was made possible by this era that never made the headlines, not because it was unimportant, but because it was foundational. So what if the boring billion isn't just our story, but the blueprint for all life in the universe? When scientists now scan exoplanets for signs of life, they ask, is there oxygen? Is there methane? Is the chemistry stable long enough to build not just organisms but ecosystems? Answering that with accuracy means understanding how Earth did it first. Voiceover. If we find alien life, it probably won't be fireworks. It'll be film. Green surface mats, glowing cells swimming blindly in red oceans. It'll be a boring billion, somewhere else. One of the quiet lessons the boring billion teaches us: stability is rare. For a billion years, the Earth had mild climates, balanced tectonics. A steady oxygen climb, no huge extinction resets. But when that balance shifted, Earth froze over. The boring billion shows us how delicate life's balance really is. Too much carbon, greenhouse collapse. Too little, global ice chemistry is king. And life itself plays a role in regulating it. Voiceover. Life doesn't just survive the planet, it shapes it and endangers it. That truth resonates louder than ever today. Humans, modern, messy, thinking, feeling humans, would not exist at all without the eukaryotic merger, the invention of sexual reproduction, the evolution of multicellularity, the quiet climb of oxygen, and all of this happened during the boring billion. You are, quite literally, the echo of forgotten cells, trying something crazy over lunchtime 1.5 billion years ago. Voiceover. Emotional. You didn't come from monkeys. You came from microbes. And they came from silence, from sunlit seas and still air, from a patience no predator could ever understand. The boring billion breaks the myth that evolution always charges forward. It retrained us to see evolution as feedback loops, long pauses, dead ends, prototypes, hiccups, moments of brilliance in oceans we'll never swim in. It was a time where slowness wasn't weakness. It was fuel storage. Survival prep base camp, the marathon, not the sprint. The Cambrian explosion. The big boom of animals, shells, predators. Monsters, one grabs all the headlines. But ask any evolutionary scientist. That didn't come out of nowhere. It was powered by what came before without Rodinia's tectonic breakup, gradual oxygen climb, microbial complexity, preceding genetic experimentation. The Cambrian doesn't happen. The same is true in any system, biological, cosmic, even social. In every story, the quiet chapters give the action its meaning. Ask a cell? No. Ask a fossil hunter? No. Ask oxygen? Definitely not. Ask a future civilization sifting through rock layers? This was Earth's longest proof of concept. And it worked. Boring is a human word. Time doesn't get bored, evolution doesn't rush, cells don't care who's watching. Today, Earth rests in another stable zone. Oxygen is high. Continents relatively calm. Biodiversity flourishing, though threatened. Humanity thrives. But the boring billion reminds us, stability doesn't guarantee static futures, complexity requires care, and evolution is a story of reaction. To planet, to chemistry, to each other. Are we still in a peaceful period, or are we nearing another shift? Are we the next Cambrian, or the next snowball? Voiceover pause. Let it breathe. Maybe Earth is waiting again. Final music swells. Emotional soaring. Voiceover from the heart. We think transformation comes in fire, flood, and fury. But sometimes it comes in a whisper. The boring billion gave us breath, blood, brain, and bones before we were even imaginations in a cell's dream. It's not a mistake. Not an accident. Not a lull. It was Earth. Becoming. Without it, you wouldn't be here. Without it, nothing would. So if you're ever asked, what happened during the boring billion? Smile and answer everything.